explain the conservation of charge or the quantization of charge? Can you differentiate between conservation and conservation of charge? Hello everyone, welcome once again to Explicit Physics Academy. I'm Coach Victor Odu, and today we'll be looking at conservation of charge, quantization of charge, and the units of charge. If you've not gotten through our previous video, please do it to rushly go and check on our last video on electricity, and you get to understand what is electric charge, the types of charges, and also conductors and insulators. We made it very simple, so do it to go back and watch it before you continue. Okay, let's dive in. Conservation of charge states that in an isolated system, the sum of the positive and the negative charge does not change. It remains constant. In any system where you find charges, you see that the charges there are constant. That means charge can neither be created nor be destroyed. So in more or less, you can see that charges are conserved. They are constant in any system. Just like we are having the conservation of momentum. I'm making reference to momentum here. When you punch in this system, as you are punching it, there is the same effect is being fed to the other side. That means momentum is conserved. So charge likewise is also conserved. In an isolated system, the sum of the charges, that's the positive and the negative charge, they are all the same at any time of the system. So that's why charge cannot be created or destroyed, only transferred from one object to the other. Charge does not just destroy. The moment there is a charge in a metallic conductor, it does not just die off like that. It's being transferred from that system to another system. So a charge does not die off. That's what you should understand. That's why when you carry a conductor that is electrically charged, it does not die off from that system. It moves to the next system. The moment you connect it to another system, charges are being induced. The same rate of charge that was found in that conductor you were holding is being transferred to the next object, and the same effect of or the same amount of capacity of charge that is present in that one, when you carry another object to place it in that one, the same charge is being charged material, but it's a good conductor of charge and of electricity. You agree with me that the same amount of charge that was found in that material will be transferred to the next material at the same rate. Meanwhile, it's still charged. That is to tell you that it will be destroyed. It can only be transferred from one place to another. So that's what conversion of charges is all about. So charges are being conserved. That means they are neither created nor destroyed, but can be transferred from one system to another. Or the algebraic sum of the charges in a system, or the sum of the positive and the negative charge in a system, does not change. It remains constant. So we are going to be looking at quantization of charge. Charge states that electric charge comes in packets, in quanta. That means it's not continuous. Quantum physics back then, while I was in college, I do love quantum mechanics, and all of that. We did a lot of Stringer's equation and Heisenberg equation, and I get to understand what it means by quantum numbers, quantization of numbers, and so on. So charge is quantized. Now, it's in discrete values. It's not continuous. So what that means is that charges cannot be found at 0.1 charge or 2.5. So electric charges are quantized. It means you will point to this as 1 electron, 5 electron, and so on and so forth. That means they are quantized. So from the board, the quantization of charge states that electric charge comes in discrete packets, that is quanta. Rather than being continuous, they come in discrete values. They come in discrete, okay, in discrete packets. The magnitude of the charge is denoted by E on the board, and whenever a physical quantity possesses discrete values, then the quantity is said to be quantized. So you should know that electric charges are quantized. They come in discrete packets, not in continuous packets. Find that the expression for electric charges are being expressed in this equation. Q is equal to NE, when Q is the quantity of charge and N is an integer number that tells us whether it's a positive or a negative. When it's a positive, we know that it's a positive charge. When it's a negative, we know that it's a negative charge. And E is the electron. Okay, that's very, very important. It's important to know that the smallest unit of charge is given by this value 1.6 times 10 raised to the power of minus 19 coulombs. It's very, very important to know that that's the smallest unit of charge is given by this value. So in case as we progress in this electrical concept in physics, charge and so on and so forth, when we enter into Coulomb's law of electrostatic, then we're looking at the unit of electric charge. So the unit of electric charge is coulombs. So from the board, Q is given by IT. I is the current, T is the time. The current in amperes, the time in seconds. That would say that in electric charge, what is the unit? So the unit of electric charge is coulombs, and it's been given by this expression Q equal to IT, where Q is the charge in coulombs, I is the current in amperes, T is the time in seconds. So from here we can say that electric charge is the rate of electric current in a metallic conductor. Is the time at which an electric current moves. That is an electric charge. So that one you should be able to understand from this point. So we've talked about quantization of charge, we've talked about conservation of charge, and we are now talking on the unit of charge. We are going to be looking at Coulomb's law, and we're going to be Coulomb's law of electrostatic, and we're going to be solving numerous problems, and also we also look at principle of superposition, and then we also saw some problems there, and then you can drop on the comment section what you think we should take back next. Thank you.